Hi friends, in this video we are going to discuss one important concept of the linear algebra, that is diagonalizable matrix. So what is meant by diagonalizable matrix? So before that I will discuss some concept what is meant by similar matrix. So for example, let's say this is my matrix A. Here I will write this is my matrix A, which is a square matrix of order n, and let's say this is my matrix B, which is again a square matrix of order n. Here I am saying this B is similar to A, means B, here this B is obtained from this matrix by applying some elementary row operation or elementary column operation. Here if B is similar to A, here if B is similar to A, if there exists a non-singular matrix say P here such that B can be written as P inverse A P. So this is the definition of similar matrices. Here B is similar to A means there exists a non-singular matrix P means determinant of P is non-zero. Determinant of P is non-zero, this matrix is invertible, that is inverse of this matrix is exists. So we can write B as P inverse A P. So here this is the definition of similar matrices. Then here we can say this B is similar to A. But here if B is similar to A means B is obtained from A by applying some elementary row operation or column operation. Here you can say or A is similar to B. So here since P is invertible matrix, here this is equal to, here can I write here B equal to P inverse AP. Since P is invertible matrix, here can I multiply P on left side of this equation, that is post multiplication, that is here pre multiplication, that is P into, here I am multiplying P on left, that is P equal to P into B equal to here P, this is P inverse, this is A and this is P. So this is same as P into P inverse is I, so this is simply A and this is P, so this is my PB. Now I want to multiply, so here now you multiply P inverse on right hand side, that is right side, so that is post multiplication. So this is P, this is B, this is P inverse, this is equal to A, this is P into P inverse, this is same as A into I, this is I. So here this is same as P, B and P inverse. So here I am writing A equal to P, B, P inverse. So here A is similar to B. So here you can say B is similar to A, means B is obtained from A by elementary operation. Now here A is similar to B, means A is obtained from B by some elementary either row operation or column operation. This is the definition of similar matrices, means one matrix is obtained from another matrix by applying some elementary row or elementary column operation. Now this is the similar matrix, that is this is similar matrix. Here similar matrices, here similar matrices. So this means similar matrices. Now what is meant by diagonal matrix? So here all of you know a matrix. For example, let's say this is matrix A. Here let's say this is matrix A. Here I will write A1 1 0 0 A. So this is 0. This is A2 2. This is 0. This is 0 0 and this is A3 3. So diagonal matrix is matrix having all the non-diagonal entries are 0. Here this is my matrix A of order 3 cross 3. So here if I equal to J, here if I equal to J, Aij position, if I equal to J means Aii, that is this A1 1, A2 2, A3 3 are the diagonal entries of this matrix A. And if I is not equal to J, that is if here this is the A1 2 position, here I is not equal to J, this is the A1 3 position, I is not equal to J, this is the A2 3 position, here also I is not equal to J. If I is not equal to J, that is the non-diagonal entries. If I equal to J, this is the diagonal entries. The definition of diagonal matrix says diagonal matrix means a matrix in which all the non-diagonal elements are 0. Means here all A, I, J equal to 0 for I is not equal to J. Here for all A, I is equal to 0 for I is not equal to J. Here for and A, I either 0 or non-zero. You can say this A, I are either 0 or non-zero. Here in the definition of diagonal matrix, here we are saying a matrix in which all the non-diagonal entries are 0. For example, here if I write, let's say this is A1 equal to, here I am writing 0 matrix of order 2 cross 2. This is the 0 matrix of order 2 cross 2. Here you can see this is the non-diagonal entries A1 2, and this is the A21 position. This is the non-diagonal entries, and you can observe here non-diagonal entries of this matrix are 0. That's why this matrix is the diagonal matrix. In the definition of diagonal matrix here, matrix in which all the non-diagonal entries are 0. There is no constraint about diagonal entries. Diagonal entries are either 0 or non-zero. We can say that matrix is diagonal. For example, this is my A1 diagonal matrix. Here I will write A2 equal to, let's say 1 0 0 1. So here this is the non-diagonal entries are 0. This is diagonal matrix. Let's say this is A3 equal to, here I am writing 1 0 0 0. This is also diagonal matrix. Here non-diagonal entries are 0, and one diagonal entry is non-zero and another diagonal entry is 0. So this is also diagonal matrix. And let's say A4 equal to, here I will write here 0 0 0, and this is 1. So here you can observe at now this time this is the diagonal entries. This is 0 A11 position, this is A22 position, this is non-zero. But you can observe one thing, non-diagonal entries are 0. That's why this is also diagonal matrix. But here I am writing, let's say A5 equal to, here 1, let's say 2 0, and let's say this is 3. Here you can observe this is the not diagonal matrix. Why? Here this is the non-diagonal entries. This non-diagonal entry, that is non-zero. That's why this matrix is not diagonal matrix. Here the definition of diagonal matrix says a matrix in which all the non-diagonal entries are 0. But here in A5 this is the non-diagonal entries, that is A21 position. This is non-zero. That's why this matrix is not diagonal matrix. Now here this is the definition of diagonal matrix. And here above you know what is meant by similar matrix. That is A is similar to B or B is similar to A. If B is similar to A, there exists non-singular matrix P such that B can be written as A. If A is similar to B, you can write this as A equal to PB P inverse. Here P is the non-singular matrix, that is determinant of P is non-zero. Here non-singular means here determinant of P is non-zero. That's why then and then only you can say this inverse of this matrix exists. Now I am going to the concept of diagonalizable matrix. What is meant by diagonalizable matrix here? So this is my A. Here I will write the D equal to, here let's say for example here I am writing any general matrix D, that is diagonal matrix. Let's say A1 1 0 0, and this is, let's say this is A2 2. Here this is the diagonal matrix, and here of course A1 1 and A2 2 are non-zero. Here I am just for sake of understanding, here I am taking A1 1 and A2 2 entry are non-zero, and this is these are the diagonal entries and non-diagonal entries, that is A1 2 and A2 1 are 0. So this is the diagonal matrix D. Now I want to define what is meant by diagonalizable matrix. So for example, let's say this is the matrix A. In the word itself, meaning height, diagonalizable means that matrix is going to be a diagonal. So here what is meant by diagonalizable matrix? This matrix is going to be a diagonal by some elementary row or by some elementary row and elementary column operation. If this matrix A is diagonalizable if A is similar to some matrix D, where D is the diagonal matrix. If A is diagonalizable, then A is similar to D. So here write the definition. If A is diagonalizable, if A is diagonalizable, then A is similar to D, means here D is the diagonal matrix. Then A is similar to, here I will write, then A is similar to some diagonal matrix D, some diagonal matrix. So D, that is here I am writing, here in word, here I am writing A is similar to D. So what is meant by A is similar to D? There exists a non-singular matrix. Here there exists a matrix P, that is matrix with determinant of P, matrix having non-zero determinant, then there exists a non-singular matrix P such that D can be written as P inverse AP. Just in place of B, here I am taking D. So here I am saying this matrix D is similar to A, or A matrix is similar to D. Here I am saying if A is diagonalizable, then A is similar to the matrix diagonal matrix D. So A is similar to means there exists a non-singular matrix P such that this D can be written as P inverse AP. So this is the this is the way to write the diagonal matrix D. Now here this is my matrix A, which is going to be diagonalizable, and this matrix D is the diagonal matrix, and this matrix P is the model matrix. So what is meant by model matrix, and what are the element of this model matrix P, and what are the element of this diagonalizable matrix D? So I will tell here this A is a matrix of order n. Here this A is a matrix of order, let's say here I will take, for sake of understanding, 3 cross 3. Here I am taking A is a 3 cross 3 square matrix, and this matrix have, let's say, lambda 1, lambda 2 and lambda 3 are the eigenvalues. Lambda 1, lambda 2 and lambda 3. So here this is the corresponding to lambda 1. Here let's say this is my eigenvector x1, corresponding to x2, let's say this is my eigenvector x2, and corresponding to x3, this is my eigenvector x3. So here the elements of D are, here I will write the D as, the elements of D are lambda 1 0 0 0, lambda 2 0 0 0, lambda 3, and elements of P means the columns of P. First column of matrix P is the first eigenvector, that is here I will write x1. This is the one eigenvector, means this is the first column of the eigenvector. This is the first column having eigenvector x1, that is the column first of model matrix P is my first eigenvector, and the column 2 of my model matrix P is my second eigenvector, and column 3 of my model matrix P is my third eigenvector. So this is model matrix P. In model matrix, first column is first eigenvector corresponding to eigenvalue lambda 1. Second column is second eigenvector corresponding to this, and third column is third eigenvector corresponding to this eigenvalue lambda 1. Now here I will write this is my D equal to P inverse AP. So here this is my P matrix. Here since determinant of P is non-zero and so P is invertible, means yes, P inverse exists. You can write here, just here from here, okay, I will write here, so I don't have space, so I will write this matrix in terms of A. So I will write so from here I will write this equation in terms of A. So here this is D equal to P inverse AP. I want to write this in terms of A. Can I multiply P on left? So this is equal to, here this is equal to, here I am multiplying P on left. This is equal to PD equal to, here P into P inverse AP. So this is equal to PD, which is equal to AP. Now this time I will multiply P inverse on right hand side. This is PD P inverse, which is equal to A. So here this is my A. Now here I am writing A equal to P D, and this is P inverse. Now this is my A. Now I want to find A square. So here A square means here A square equal to A into A. So this is simply A means P D P inverse, and this is P D P inverse. Just put 2 times. So this is equal to, here P, just open this middle bracket, D, here P inverse into P, which is equal to D and P inverse. This is same as, this is P and D, here P inverse into P, this is I. Here I will simply write this is D and this is P inverse. This is same as P D square and P inverse. So this is my A square. Now I want to find A cube. So here A cube equal to A square into A. So just put the value of A square is, this is P D square P inverse, and this is P D P inverse. So this is equal to, just open this middle bracket, P, here this is D square, and here this is P inverse, and this is P, and this is simply D, and this is P inverse, which is equal to, here this is P D square. Now this P inverse into P is I, and this is simply T, which is equal, so which is, and this is P inverse. So this is same as P D cube and P inverse. So here this is my A cube. So in this way, for any n, here I am writing A power n can be written as P D power n, and this is P inverse. So you can find power of here A power anything. For example, you can find A power 10, A power 20, A power 30. You can find anything. Now, how this is easy? Now, here this is the D is the diagonal matrix having all entries, means having entry on the diagonal along its diagonal are eigenvalue. Here I will write. I hope all of you write this. Here I will write this expression again. So this is my A power n equal to P D power n and P inverse. So here all of you know the matrix P, means P is the matrix with first column is first eigenvector, second column is second eigenvector, and third column is third eigenvector. Now here D means, here D is the matrix with D is the diagonal matrix, means if D is the diagonal matrix means all the non-diagonal entries are 0 and diagonal entries are the eigenvalue. Let's say here I am writing for 3 case, 3 cross 3, lambda 1 0 0 0, lambda 2 0 0 0, and this is lambda 3. So here D is the diagonal matrix, means all the non-diagonal entries are 0, and along the diagonal this lambda 1, lambda 2, lambda 3 are the diagonal entries, and these diagonal entries are the eigenvalues of this matrix A. Here I will write lambda 1, lambda 2 and lambda 3 are the eigenvalue of my matrix A. So here this lambda 1, lambda 2, lambda 3 are the eigenvalues of matrix A, and this is my diagonal matrix. So all of you know, if lambda is the eigenvalue of A, then the result is, then lambda power n is the eigenvalue of A power n. So here I am using this for D. So in the same way, here if lambda is the eigenvalue of, in place of A, here I will write D. So here if lambda is the eigenvalue of D, then lambda power n is the eigenvalue of D power n. So here I will write this D power n in terms of, here this, by using this property. Here D power n means just simply this is same as lambda 1 power D, lambda 1 power n 0 0 0, lambda 2 power n 0 0 0, lambda 3 power n. This is my diagonal matrix D. Here you can write just, therefore A power n can be written as, here this is P, this is my P matrix P, and D means, here you can write just D power n, this above matrix, and this is my P inverse. So I will write here. So you can write here P is simply this matrix and P inverse is, so just find the inverse of this matrix. Now so this is my A power n. Now here just now we have learned what is meant by similar matrices. Here I will define. Here if A is similar to B, here if A is similar to B, then there exists a non-singular matrix P, that is determinant of P is non-zero, such that B can be written as P inverse A P. So here in the same case, here if this A and B are orthogonally similar, here I am writing if A and B are orthogonally similar, that is here I am writing, let's say this A is similar to some diagonal matrix B which is orthogonally. So orthogonally similar means there exists a orthogonal matrix. Let's say P such that B can be written as P inverse A P, and this P is my orthogonal matrix. So here since P is orthogonal matrix, since P is orthogonal matrix means P into P transpose is equal to I. So this implies P transpose here equal to P inverse. So here use this in this expression. So here therefore D can be written as P inverse in place of P inverse P transpose. This is A and this is P. So here, so for example, if you have a matrix A, so if they ask orthogonally similar, so we have to, so first they will give the one matrix A of order 3 cross 3, for example. So corresponding to that matrix you have to find the eigenvalue. Corresponding to each eigenvalue you have to find the eigenvector. So by using that eigenvector, first eigenvector is the first column of your matrix P, that is your model matrix. Second column of your model matrix is second eigenvector. Third column of your model matrix is the third eigenvector. Now this is my matrix P. Now we have to find the inverse of this matrix. So to find the inverse is very again time taking. So if this is similar to D orthogonally, just take means D can be written as P inverse AP. That is, there exists an orthogonal matrix. That exists this P matrix is orthogonal. What is meant by orthogonal? P into P transpose is equal to I. Just P transpose is equal to P inverse. Just take here instead of finding P inverse, instead of finding instead of finding this P inverse, just take the transpose of. Why? P inverse is same as P transpose. Just take the transpose of this. So here I will write. Just take the transpose of this and write A, and this is P. Just multiply these three matrices. You will get diagonal matrix D. Here this is the diagonal matrix having all the non-diagonal entities are 0 and diagonal entities are eigenvalues of this matrix A. So by using this you can write A power A in terms of by using D and P. So this is the, you can find A by using this model matrix P and diagonal matrix D. Here for any power n, for example, let's say here I will write, so for example, let's say this is my matrix A, let's say this is my matrix A having, let's say 2 0 0 and let's say 5. So this is the matrix, and you can say eigenvalue of this matrix are lambda 1 equal to 2 and lambda 2 equal to 5. So here I will build D as here lambda 1 equal to 2, that is D 0 0 and 5. So here if I want to find the, here A can be written as, from here A can be written as P D and this is P inverse. So here find the eigenvector, let's say find the eigenvector x1 and x2, and this is my matrix. Here this is equal to P. So here P is the matrix having, here I will write here let's say this is the P matrix having eigenvector x1 and let's say this is the eigenvector x2. So after that write A equal to, here I will write P D power n and this is P inverse. So here I want to find, so let's say this is A power n. So here I want to find A power 2025. Let's say A power 2000. Let's say A power 2025. This is same as P, here D power 2025. This is P inverse. This is same as, write P as it is, and here write this D means, here I am writing 2 to the power 2025. This is 0, this is 0, and 5 to the power 2025, and this is just P inverse. So this is my A power 2025. So in this way you can calculate power of anything by using this model matrix P and diagonal matrix D. So this is all about diagonalizable matrix. Now we have some properties. When we say that the given matrix A is diagonalizable, so here I will write. So here first property set is not property. This is the complete result. Here let's say if A is a matrix, let's say if A is a matrix of order n, if A is a matrix of order n is said to be diagonalizable, if and only if A possesses n linearly independent eigenvector. So the second result is, that is note here, if eigenvalue here eigenvalue of a square matrix A are distinct, then A is diagonalizable. Then A is diagonalizable. So, and third is, every real symmetric matrix is diagonalizable. That is, every real symmetric matrix is diagonalizable. So here these are some notes, that is these are some results. So here I don't prove these results. So now we discuss the working rule for the diagonalization of a square matrix A. So here how to convert the given matrix A into the diagonal matrix D. So here I will write. So all of you know this is here. First I will write here working rule to find the diagonalization of a square matrix A. So working rule to convert the given matrix into the diagonalizable matrix. Here first rule. So for example here let's say the first rule, find the eigenvalue corresponding to find the eigenvalue of that given matrix A. So here first rule is find eigenvalue of a square matrix A. Square matrix A. So here find the eigenvalue. After finding the eigenvalue, find the eigenvector corresponding to each eigenvalue. So second is find eigenvector corresponding to each eigenvalue. So say here I will write say x1, x2 and x3 and so on. So find, so for example if you have 3 eigenvalue, find the eigenvector corresponding to eigenvalues, that is find x1 corresponding to lambda 1, find x2 corresponding to lambda 2 and find x3 corresponding to lambda 3. So here third rule is find model matrix P having normalized eigenvector as its column. So here so just now we have discussed model matrix P. Here the first column of your model matrix is eigenvector x1, the second column of model matrix is second eigenvector, and the third column of model matrix P is the third eigenvector. Here what is meant by normalized eigenvector means length of each. Here norm of x1 is 1, here norm of x2 is 1, norm of x3 is 1. Here say I will write that is P equal to here x1, here I will write this is x1, this is x2 and this is x3. Here if this is the normalized means length of x1 is 1, length of x2 is 1 and length of x3 is 1. So keep as it is. Keep as it is this model matrix P having column 1 is eigenvector x, column 2 is eigenvector x and column 3 is the eigenvector x3. So if here keep as it is, if norm of x1 equal to norm of x2 equal to norm of x3 which is equal to 1, and otherwise so write P as here x1 divided by norm of x1 and second column x2 same as norm of x2, third column x3 divided by norm of x3 means here let's say if you have a vector x, let's say if you have a vector let's x, here I will write, let's say x1 is, here I am taking 1 0 0. You can check this norm of x1, that is norm of x1 is same as under root 1 square plus 0 square plus 0 square, which is equal to under root 1, which is equal to 1. Why? Plus minus 1, but here this norm is length, so here length is never negative, that's why this is the norm of this vector x1 is 1. Here no need to do anything, just write x1 as x. If let's say this is your, let's say vector x2, having here I am taking 2 0 and 0, and you can check this norm of that x2 equal to under root 2 square, that is 4 plus 0 square 0 0, which is equal to under root 4, which is equal to just 2. Here I am taking the positive only. Why? This is the length. Now here norm of this x2 is 2. I want to convert this vector into the normalized. Here just divide this x2 by length of this x2, which is equal to, here now this is 2 by 2, this is 1, this is 0, this is 0. Here now you can check, let's say this is my x2 dash, so you can check length of this x2 dash is 1. So here if this vector x1 x2 x3 is normalized, no need to do anything, just write p. First column is first eigenvector, second column is second eigenvector, third column is third eigenvector. So here this is your model matrix P. Now here fourth is find the diagonal matrix D. Here fourth point, here I will write here, fourth point, find diagonal matrix D, matrix D, as D can be written as P inverse AP. So here write D can be written as P inverse AP. Here if this D and A are orthogonally similar, that is if if A and this D are orthogonally similar, there exists this P. Here now determinant of P is non-zero, that is non-singular P, such that this P is orthogonal such that D can be written as P inverse AP. Here since P is orthogonal, therefore P into P transpose equal to I, so this is same as P transpose equal to P inverse. So here I am writing, therefore D equal to P transpose here AP. So here this is the working rule to convert the given this is the working rule for diagonalization of a square matrix C. So here first find the eigenvalue, find the eigenvector corresponding to each eigenvalue, then form the model matrix P. So check whether the eigenvectors are normalized. If not, so make this vector, that is x1 dash, x2 dash, x3 dash normalized, and let's say this is the P, that is model matrix. So find the diagonal matrix D by using this equation, D equal to P inverse AP. Here P is the model matrix and A is your original given matrix, and here this D is the diagonal matrix having diagonal integer eigenvalues of your A matrix A. So this is the working rule to convert the given matrix into the diagonal matrix, that is diagonalization of a square matrix. Thank you.